Welcome back. In this set of slides, I'm going to be talking through the ideal of fairness as it applies to AI systems, and in particular, machine learning systems. And the way I will pose this, the main question here is, when is a decision-making system or procedure a fair one? What should be our standard of fairness? And we might end up selecting different standards depending on what the task is, what the particular application of an AI system is. But to start out, there is this little typology of standards of fairness. There are basically two main categories, statistical and causal. So statistical fairness concepts define fairness in terms of the distribution of some feature, or for instance, the distribution of predictions or the distribution of accurate predictions across groups. And so at least in the paradigm case, that's what the statistical approach does. There's also an individual's approach that uses statistical procedures too, but that's the kind of paradigm case. And this is the one that's used most often. You want to find out if the true positive rate and the false positive rate are basically equal between two identifiable demographic groups. If your system has a higher false positive rate for women than for men, or for non-white individuals than for white individuals, these are signs of bias and of unfairness. And so you want to avoid that. The other approach is a causal approach. And this is a little bit harder to summarize, but the basic idea is you want to somehow be able to test that your systems aren't making predictions in an unfair way, that your systems aren't relying on information, for instance, that they shouldn't rely on when they make their predictions, that relying on that information or making predictions on the basis of that information is unfair. So, for instance, if you had a system that just automatically marked someone as a greater crime risk if they were non-white, then that would be a system that could be criticized by a causal fairness definition, because you might say that that system is behaving like a racist parole officer, for instance. It's behaving like a racist human in that it's overtly discriminating based on race. But there can be cases where these systems are very like they're pretty clearly statistically imbalanced. Even if you can't identify a causal source, you may not know exactly where the causal source of the discrimination or the unfairness is. And there may not be a single causal source of the discrimination or the unfairness. But if the results, by virtue of your statistical analysis, are some kind of unequal, difference in false positive rates, for instance, between identifiable groups, that's normally taken to be a pretty strong argument that your system is unfair somehow. So these are two main big categories. And then within the statistical group approach, I'll come back to talk about the statistical individual a little bit later. Within the statistical group approach, you have a variety of standards that have been offered. And basically, these are standards for what should be equal between groups in order for the system to be considered as fairly treating individuals in both of those groups. So I've tried to capture some of the main features of those fairness standards on this slide. And the basic idea here is that, there are three main categories of fairness metric within the statistical group approach. So one of these is just whether the number of predictions, or the percentage of predictions or classifications of a certain type. These are predictions or classifications made by the AI system. Whether the percentage is the same across demographic groups. And if it is, then they're fair by that metric. And if it's not, then the system is not behaving fairly by that metric. So this is called statistical parity. Sometimes it's called demographic parity. And it's it's an intuitive measure of fairness, but a problem with it is that there may sometimes be good reasons to have more classifications of a certain type for one group than for another. For instance, suppose that a particular profession is more prevalent within one demographic group than in the other. Then it might be that ads targeted towards individuals in that profession, it makes sense. It makes sense that there's a disproportionate number of ads targeted for a particular type of job in one group than in another group. And so in these cases, statistical parity seems like it's the wrong measure because it would require that exactly the same proportion of predictions be made for every group, when that isn't always what actually is most accurate as a description of that group, or as a recommendable response or recommendable behavior in relation to that group. So the other two options here are designed, or they have built into them the ability to be more subtle in how they in the number of, or the percentage of predictions or classifications of a certain type that are made between groups. And the difference between them is that one of them is, so they both have to do with accuracy, okay? And so they have to do with whether or not the predictions or classifications were accurate. And the basic idea in both is that you want the same level of accuracy across any demographic groups that you're comparing. You don't want the system to be more accurate in its classification of Caucasian Americans than it is in its classification of African Americans, or more accurate in its prediction of men than it is in its predictions about women, okay? But accuracy is not just a single notion. There are two basic kinds of accuracy. So one is whether, given a particular prediction score, the individual that's given that prediction score has the predicted attribute. That's what's called predictive accuracy. The other type of accuracy has to do with false positives and false negatives. And the question here is, among those who have the particular attribute, how many of them are correctly predicted by the algorithm? And believe it or not, those can come apart. Those types of accuracy can actually lead to different scores. If you score the same system by each of those two metrics, you can very often get different scores. In fact, not only do you very often get different scores, but you almost always get different scores. And this was discovered in the process of debate about a recidivism prediction algorithm called Compass. So recidivism is basically when someone who's been charged with a crime is then charged with another crime. They're sort of brought in again, they're arrested again within a certain period of time. So this Compass algorithm, this was a algorithm that was trained on, I think, tens or maybe hundreds of thousands of, probably tens of thousands of survey responses. 137 questions to a survey and other information about an individual, and think of it as a kind of neural network architecture. The system, the Compass algorithm, was trained to predict whether or not an individual, based on their survey responses, would recidivize or not recidivize within a 2-year period. That is, would they be arrested for another crime within a 2-year period? And so in 2016, this system was widely used, particularly for deciding upon whether an individual would be released on bail, whether they would be detained because they were thought to be a risk of further criminal activity in the interim between when they were originally detained and their trial date. And so this was used in the criminal justice system for that, and for other purposes, sometimes used for parole hearings. And in 2016, some researchers for the online magazine ProPublica did a fairness analysis of Compass, and they found that the false positive rates for African Americans, for Black individuals, was twice that, roughly, of white individuals. In other words, a given any given Black individual who's being rated by Compass, that individual was twice as likely to be rated a recidivism risk when they weren't than a white individual would be. And that seemed like a very strong mark of unfairness. And conversely, the false negative rate for Caucasians was almost twice that of the false negative rate for African Americans or Black Americans. So this was thought to be a very strong signal of unfairness. But soon after this analysis from ProPublica was published, some of the researchers that had been involved in development of the COMPAS algorithm argued that that was the wrong fairness metric to use for evaluating COMPAS, and that in fact its predictive accuracy was equivalent between groups, or close enough to equivalent to be counted equivalent. So that's the PPV score there on the screen. And so what that says is, for an individual who receives a certain risk score, how likely is it that they will recidivize? And it turns out that that number is the same between African Americans and Caucasians. So if you're scratching your head at this point and saying, wait a minute, how can that be, right? Welcome to some of the glorious apparently paradoxical results of statistics. Statistics is that way sometimes. It seems like it shouldn't be that way, but it is that way. And in fact, soon after this debate had erupted, some mathematicians showed that it's almost always the case that these two fairness metrics diverge. This is known as the fairness impossibility result. And the only exceptions, that is, I said it almost always the case that predictive accuracy and the false positive, false negative measures diverge. Which is EO on this slide, that the only exceptions to when they diverge is when the base rates are equal between the groups, that is, the recidivism rate is equal between the two groups, or when the machine learning algorithm that's trained up is able to predict what will happen with perfect accuracy. So both of those conditions are extremely rare. And so they're extremely rare. So this just showed that almost always we're dealing with this phenomenon of fairness impossibility. Now, at this point, I want to, introduce a question. And I think this is interesting because this is a question that really we couldn't ask about fairness until an analysis of fairness had been done at this level of specificity. And as it happened, that didn't occur until the development of AI ML systems and the efforts to evaluate them. So now we have a deeper understanding of this concept of fairness than we did before, but we're faced with a challenge as far as what we should do about this incompatibility. And a number of responses have been offered for what should be done about fairness incompatibility in AI ML systems, and I've summarized these on the slide here. There are some arguments that fairness impossibility is overplayed for various reasons. I won't go into the details of that. Some people try to find a kind of middle ground between the metrics. So they try to sort of negotiate or kind of trade off between the metrics and select the right middle point. A simple way would be to just sort of take all three metrics and then just take the average score across all three. I tend to think that's pretty flat-footed because there's not really a good justification for that except for us just not knowing what to do about the impossibility problem. So we could do that if we really want to get a number and we just have no idea what to do, but it's not really addressing the problem in its own terms. And then a third option is to select one of those metrics as particularly relevant for a particular case. So one point there is that sometimes false positives are really important. We want to minimize false positives, for instance. If the intervention is one that could hurt someone, then we generally want to minimize false positives because we want to sort of minimize the number of interventions we do that are mistaken. On the other hand, if it's allocative, if it's about providing assistance, we might want to minimize false negatives. That is, we want to make sure that we don't miss anybody who could potentially be helped by the allocation. So selecting the right metric, and in yet in other cases, statistical parity may be the best choice. For instance, cases where it's not really about who deserves the allocation, but you want to make sure that the allocation is spread equally across groups, then statistical parity would be a good choice. So, kind of picking the metric based on context seems like a pretty compelling response to the problem. Another option is to leave the decision up to, say, democratic deliberation. So just say, hey, we have these recidivism prediction algorithms. Which do you care more about, minimizing false negatives or minimizing false positives? Do you want to take the risk of holding some people over in, without bail that are innocent just because or aren't going to commit another crime just because we want to make sure we're safe? Or do we want to run the risk of releasing more people some of whom may commit crimes, but we're more certain that we're not holding anybody who doesn't need to be held? And so maybe those are decisions that should be made by the populace or the society rather than by AI algorithm trainers and designers, right? So maybe we leave that up to the society to decide. Some other options are to break with the whole group fairness paradigm. So some have argued that the fundamental problem here is that group fairness doesn't include a consideration of what the causes are of the classifications. And so we really need to move from a group fairness perspective to a causal fairness perspective. The individual fairness perspective is kind of connected with that. There, the question is, for any given individual, is every other individual who is similar treated in a similar way? And so it's not really comparing across groups so much as it is comparing individual to individual. But unfortunately, it also seems to be harder to do mathematically than group fairness. So we don't really have a tractable way to do that yet. And then finally, we could just stop using systems that are unfair by any of these standards. But the problem with that is that fairness impossibility is baked into decision making. It's not actually a problem that's unique to AI ML systems. It's something that applies whenever we're trying to evaluate the distribution of decisions across two groups. And where the base rates are not equal and where we don't have perfect predictive power. In those cases, the distribution of decisions, if it's fair by one of these standards, it's not going to be fair by one of the others, according to fairness impossibility. And so, yeah, where this is a problem that just has to do that we realize now applies to our decision making in general when we consider that across many cases of decisions made, and it's not just a problem with ML systems that we could turn off by turning off the ML systems. So where do you stand on this? I mean, among these possible answers, which seems most compelling to you? That's a question I will leave you with. It's a question that the whole field of AI ethics has been left with basically since 2016 when this problem was first discovered.